I'm Megha Mishra, and today I'm going to be discussing the second Physics 2211 lab regarding the motion of a falling object. To start, the purpose of the lab was to observe the motion of an object that is dropped from rest and falls somewhat slowly and straight down, and then compare these observations to two computational models. Both models are based on Newton's second law. One only considers the effects of gravity, while the second considers the effects of both gravity and drag. The results of this lab will show us that the second computational model more closely mirrors the observed motion of an object falling in the real world. I'm going to take a moment to briefly overview main physics concepts that are associated with this lab. Like previously stated, both computational models are based on Newton's second law, which concerns the system and its surroundings, specifically in the sense that the force that acts on the system from the surrounding results in the changes of momentum. In our specific experiment, we chose to drop an expo eraser, so that's our system, and the surroundings are everything else in the room. Here you can see the equation of the momentum principle, which summarizes Newton's second law. Since Newton's second law concerns net force, we can define net force as the sum of all forces acting on the object. Unlike Lab 1, the net force in this experiment is a non-zero value due to the presence of both drag and gravitational force. Drag is a force that acts opposite the relative motion of a moving object and has a magnitude that is proportional to an object's speed squared. You can see the equation for drag here. Gravity is the other force that comprises our net force, and it can be defined in this scenario as the acceleration of a falling object at or near Earth's surface. The equation is seen here. Once we have that, we can start our actual experiment. To obtain the observed data, I filmed an expo eraser being dropped from rest. Using Tracker, we can then set the axes as seen by these pink lines, which allowed us to define the initial position of the eraser at 0, 0, 0. From here, the object's falling motion was tracked frame by frame, allowing us to obtain observational data for a position versus time graph for the y component, which you can see here. After the tracker data was collected, we could create the first computational model using GlowScript. We set the initial position of the object at 0, 0, 0, just like in Tracker, and the initial velocity at 0, 0, 0 as well, because the object is being dropped from rest. We start at time t equals 0 seconds and use delta t of 0.033 seconds, which is also obtained from Tracker. G is constant, is 9.8 meters per second squared, and j hat is the unit vector for the positive y-axis pointing up. Now we can focus on the while loop. Net force, in this case, only comprises of the force of gravity, so we make a variable called Fg and set it equal to the equation for gravitational force. From there, we can update the object's velocity using the velocity update formula, and then update the position using the position update formula. From this code, we obtain a position versus time graph that looks like this. We can compare this graph, which is shown here in pink, to the data obtained from Tracker, which is in purple. As you can see, initially, the two graphs are quite close to one another and increasingly differ as time goes on. From this, we can infer that gravity is not the only force acting on the object in the real world, so we can move on to our second computational model. Creating the second computational model is quite similar to the first. The only initial value we need to add is the proportionality constant b, which I obtained from running the code until I got to a final position value that was relatively close to the observed data. From there, we need to add the drag force, or FD, into our code, which can be seen here, and then update the net force to be now equal to the force of gravity plus the force of drag. And we're able to obtain a second set of predicted data. As we can see from the full comparison of all three data sets, the computational model that considers both gravity and drag is considerably closer to the observed data than our initial model. This is because in the real world, both of these forces will be interacting with falling objects, not just gravity, so this model is much more realistic. We can conclude that drag force does have a significant role in the motion of an object that's falling. However, this computational model is not perfect. There are some discrepancies in regards to this model versus the observed data, especially towards the end of the time frame, perhaps due to sources of error like the poor quality of the video obtained in the experiment. It was difficult to see the eraser as it fell, meaning that the tracked portion of the object may have differed slightly between frames. The video was also slightly shaky, so the axes may not have been perfectly aligned, which can further explain the differences. We can conclude this lab by asking some further questions. Looking at the velocity versus time graph of the two models to see which predicts a terminal velocity, which is when the force of drag pointing up is exactly balanced with the force of gravity pointing down, meaning that the net force is 0 and velocity is constant. The graph shown on the left is the model without drag, and the one on the right is the model with drag. From these graphs, we can see that velocity versus time for the model including drag starts approaching a constant value as time goes on, meaning that it's reaching terminal velocity. And if the object was thrown downward instead of dropped from rest, given that we're still including drag, it will still reach terminal velocity. To prove this, we can run a GlowScript code with an initial velocity of -1 in the y component. The velocity versus time graph this leads to is shown on the right, showing that velocity still ends up being constant over time, thus reaching terminal velocity, and in fact does so faster than when dropped from rest. In summary, the computational model that includes drag more closely resembles real-world scenarios than the one that only takes gravity into account. And having a more accurate net force means predictive models are more accurate. Thank you.